Okay, so this is the part that I'm going to discuss in this class. It is up to you. So what is the circuit is you want to write a program for that one, or shall I do it one by one? Because it will take some time. The lab technician has to do some work on that one. So I'll go one by one. Okay, if time permits me. Okay, so please take this particular information, and when time comes, then you can implement that one in lab, the tool. Okay. And then one more thing. Okay, so let us first write a Verilog program for the full adder. Okay, so let us write Verilog program for 1 bit full adder. So 1 bit full adder. Okay, so let us write how do we write a Verilog program for this one? Okay, it's very easy. First of all, we should know whenever we want to write a Verilog program for a particular digital circuit, first we should know what is the block diagram of that particular circuit. Okay, so as all of you know that what is the input size for this full adder? For example, it's a full adder. For example, FA is means the full adder. So we have A is one input, B is one input, C is another input. So, okay, A is one input, B, C is another input. It has got two outputs, as everybody knows that sum output. Okay, sum, and the next one is carry. Or I can simply write a C out. Okay, I'll simply write C out. Okay, so if you want to write a gate level modeling, everybody knows that. Okay, so as I mentioned previously, so gate primitive statements are important. Gate primitive or gate level circuit is required. As simple as that. If you want to write a gate level modeling, gate level circuit is important. Gate level circuit is required. So from the digital electronics point of view, everybody knows that. Okay, so we have to develop the equations for the sum. Sum is equal to A exclusive B exclusive C, and the C out is equal to AB plus BC plus CA. Everybody knows that one. Okay, so from this equation, we can develop the hardware. Okay, so therefore, what is the inside of this particular hardware? So that is based on these equations. Okay, so I'll write the circuit diagram here quickly. Something's happening. Okay, so here the 3 input and the gate is so 3 input XOR gate is required. It's called A, B, C, and 3 AND gates are required. So this is connected here, this is connected here, this is connected here, something like this. So it is actually the first one is A, the second one is B. Okay, for the second one is B is connected here, and C is also connected here. For the third one, A is connected here, C is also connected here. So this is what actually we can see for this one. Okay, so right here. So these are nothing but A, B, C. This is some signal. This is called C out signal. Okay. Now, so this is what inside of the circuit, right? This is what inside of your circuit. I think it's better to know right colors here, so that it is very useful for you. Okay. Fine. So therefore, the gate level circuit is there in our hand. So we can write a Verilog program for this one very quickly. So please try to understand how to write a Verilog program in the gate level modeling. Okay. So in the previous class also we have seen that every gate level mod, every Verilog programming started with module keyword because we treat the black box as a module. So therefore, I'm going to write a module is the keyword, a lowercase letters we have to use. Okay. And let us give the name of this one. It's a user defined. So whatever the name that you can give, it's possible to give. Okay. I'm writing interested to write FA. So underscore gate level, or I can write it gate level modeling is something like this. Gate level modeling, GL, gate level modeling. So for easy to understand or easy to recollect that name, for that reason I'm using this way. Okay, so what is the external view of this one? I need to write here. Okay, those who are not able to understand previously, please try to understand now itself. Okay. So what is the variables that we are using for this external device? We are talking about this device. Okay, what is the external view that we are doing here? A is one variable, B variable, C variable, sum variable, and the Cout variable. Okay. So these are the different variables I'm using. Okay, it's up to you. For example, A input, B input, C input, something also we can write it, but it is the easiest way that we can write the Verilog program. Okay. Next one is we need to define among these particular variables whether those are input variables or output variables. So we can understand here is that these are all input variables. So these are all output variables, right? So therefore I can define those things. So out of these variables, inputs are A, comma B, comma C, right? So we have to write the lowercase letters only because whatever the way that we write, for example, here if you write capital A, then only we have to write a capital A. We are allowed to write capital A. Otherwise, we should not write. Please remember the point. Okay. So it's a case sensitive. Verilog is a case sensitive. So as you can see that it's a small c that I have used. So small c only I have to use. You should not write a capital C. Okay. Please try to understand. The next one is an output. Okay. So outputs are nothing but sum and Cout, right? So this is the second step. So whatever the big circuit it is, whatever the large circuit it is, it doesn't matter. Just you have to identify that. You treat that as a black box. So you have to identify that what are the input signals, what are the variables you are using for the inputs, what are the variables you are using for the output. That's all. Okay. So and what is the internal to the circuits that is depending upon what type of modeling style that you are using. Okay, so you're using the gate level circuit. You know that the gate level circuit is there in your hand. Therefore, gate level modeling is sufficient. So let me write the gate level modeling for this one. Okay, before going to write that one, so I better to write the numeric nature for each and every gate. So that is G1. Okay, it is not necessary, but it's better choice. G3, G4, G5. Okay. So we can directly call this exclusive OR gate into your main program with the help of keyword XOR. XOR is a keyword that is used for the exclusive OR gate. Okay. So what is the name that we have given? G1 we have given. So what are the variables that I should write here? So that means within this bracket, we should mention what is the output first. What are the inputs that we are using for that particular gate? What are the outputs that we are writing here? What are the outputs that we are writing here? First, what is the first output? What is the output for that particular gate? G1 gate, sum, as you can see. Sum is directly connected to that one. Okay. So therefore, I can write sum is my output. So here you can see S is a capital letter that I have used for usual practice that I have written. But its best choice is you have to use those lowercase letters only. Sum. All are lowercase letters only. Please identify what I'm doing here. Sum is a small letters only I'm using. Next. So what is the input for this one? A is one input. Next B is one input. C is another input. Okay. So this is how we have to write Verilog program or gate level primitive statement. It is called a primitive statement, right? It is called a primitive statement. Gate primitive statement for that one. Similarly, we have another gates are also available. So we write directly. If it is an AND gate means AND keyword that I have to use. The name of the gate is C2. Okay, so what are the variables I'm using? So for if you are calling a particular gate as a primitive, okay, we should write first output, then we have to write inputs. So please remember this point. Okay, so for this particular gate, what is the output now? So is there any name for this particular gate, this particular wire? It is not directly connected to the output. It is internal to the circuit, right? So we did not mention any name for that one. So let us write the name of this one is T1, for example, right? So therefore, let us write here is a T1. Okay. Then what are the inputs for that one? For this one, we can see that A is here, B is connected here. Okay. So A is connected there, A is connected there, B is connected there. Next, we have another AND gate. Okay. Therefore, AND gate that is called C3. Okay. What is the name that we have given for this one? There is no name is there. Therefore, let me write this one is T2, for example. Okay. Similarly, I'll write this is also, it is internal to the circuit. Better I write in this green color so that it is visible. So that is called T3, for example. So therefore, this is called T2. Now inputs for this one is B comma C. So it's not a problem that you write first A then B. Then if first write C then B. It doesn't matter. Okay. So just it identifies that the gate has got one input, sorry, one output, and it has got two inputs. That's it. Next, we have to write another AND gate that is called G4. We write the name of this gate is the output for this one is T3, as you can see there, and C comma A are the inputs for this one. That's it. Oh, okay, another gate is also there, right? So finally, we have to write G5 also. So G5 is R means small r. So don't write that A and end capital letters that you should not write. Okay, this is also not acceptable. Okay, something like this. A and D also is not acceptable. These are all not acceptable. So only acceptable keyword is A and D end. That's it. Small letters all. Okay, if you anybody write like this, so it will be wrong. Okay, so please identify that issue. So for R is a keyword for the OR gate. It is G5. So what is the output for this one? C out is directly connected to the G5, right? Therefore, C out. Next inputs are, as you know that, T1, T2, T3. Okay, so that's it. But one thing we have to write, T1, T2, T3 are internal to the circuit, right? So we have to mention those variables are also as some type of data type, so that the simulator will identify that yes, there is a variables are available there. Okay, so for that one, I'm going to use these variables. That variable is actually a wire. Wire we have to use internal to the circuit. Whatever the internal wires are there, those things are called wire data type. Okay, so those are all T1, comma T2, comma T3. So that's it. So is it clear to all of you how to write a Verilog program? So finally, we have to write end module also. Don't forget to write this one. So end, don't give any kind of space. Yes, end module. So this is how we have to write a Verilog program for the AND gate. Sorry, full adder. Is it clear to all of you? Is there any doubt regarding to how to write a gate level modeling for the circuit? So it's a very basics. So if you know these basics, then only you are able to write a program for any other complex circuits. Okay. So therefore, once if I'm able to write this one, we can write any program, whether it is a, as you can see, it's a decoder, it's encoder, it's a multiplexer, it's a comparator, it doesn't matter. Once we have a gate level circuit, we have to write a gate level modeling in this way only. Okay. So if you have any doubt, please take 1 minute time, then please ask me the doubt. If you have any doubt related to that one. Please take some time and please let me know if you have any problem related to the gate level modeling. So don't say that, sir, I don't know about the gate level molding. I'm unable to write the Verilog program for the gate level, unable to write the gate level molding. Something like this. You don't say any kind of words, something like that. So very simple. 4 steps are there. So this is the only one. First step is there. So declaration is the second step that we have to know that. The third step is so what is the internal circuit for this one? But don't forget about write and merge. So only the 4 steps are there. Okay. So whenever we have internal related circuits are there, then we have write in this way. Clear? So you can also type it in the chat box also if you have any problem. If you don't have any problem, I'll go forward. Okay. Okay. Now fine. Now it's very important to think about this one is how do we test this particular adder? Okay, how do we give the inputs for the A, input values for the A, input values for the B, input values for the C, and some and C out we need not give the any kind of values because the simulator has to generate or the circuit has to generate the sum and C out. But our responsibility is that we have to give the values for A, B, C, right? So for that one, test bench is very important. So we have to write a test bench for that one. So you have to practice how to write a test bench. As I mentioned that 4 or 5 steps are required. So we have to identify those 4 and 5 steps only. And we have to apply for any circuit. Okay. So let us write that circuit. So it is better to copy this one and I want to modify there itself. Okay. So that you are able to understand. So let us write a test bench here. Okay. So for writing the test bench, I have to keep the name here is. So better I write here is one word. Source code. What we can call it, this is the source code. Our source code. Okay. Now this one is test bench. This is test bench. Okay. So therefore, normally we can call it as a source code. Whatever the design is there, that we can call it as a source code. The program description we can call it as a source code, and the test vectors we can write it that is called as test bench. Okay. Please remember that point. Okay. Now, so very simply we can write it here. So whenever you're writing a program for the test bench, you please understand that. Okay, so this is also a black box. This is also a black box. It's a test bench. Test bench. What is its responsibility? It has to generate the necessary signals for the module. Okay, so test module. So we have a test module that we have. We have a source code is there, or test the design is there. So its responsibility is that it needs A signal, it needs B signal, it needs C signal, right? Needs all these things. 1, 2, 3. So therefore the test bench is producing these kind of signals. Therefore A it is producing, B it is producing, C is producing. Right? So in that sense, we normally consider that the test bench doesn't require any kind of input and output information. Okay. So better I'll write it is a test. Just you can give the name of the module for the test bench. So therefore, you can understand that here is what is the name that I have given for this test bench now. As you can see, what is the test bench name that I have given? So FA underscore GL underscore test. Something like this, I have given the name for this one. Okay. And we have to, so this is the first step that we have to remember. Okay, this is the first step. The second step is whatever the inputs are there, those inputs we are treating as registered data types. Registered data type, reg, is the keyword that we have to use. The next one is output can be treated as wire data type. It is called wire data type. Why it is called register, why it's called why it is wire, why it is register, all these things we have discussed in the course, but we have to keep in your mind that So A and B as always need to be changed. Okay, so values will be stored and it will be always changes. Okay, in that situation that we have to use the register data type for the A, B, C. For the Y means the output is connected to only the it is not able to store the information, just to transfer the information without storing any kind of information. Okay, so you have to keep like that only. So it doesn't require the internal circuitry related information. It doesn't require any kind of design related issues. Okay, so how we are designing it doesn't matter, but instead whatever the description that we have done here, that is treated as a module directly we can write. So what is the name of the module that we have given? So whatever the program is there, the program we have to write here. Instead of writing the entire program, just the name of the module is sufficient. So this name of the module is sufficient. Okay. So therefore, let us write that name of the module. So here is FA, same name that we have to use, underscore GL. Underscore GL. Therefore, this is called, we can call it as. It is actually FA underscore GL. So what is this name of this module? Let us consider M1. Okay. So let us consider this is M1. Similarly, in previously we have written G1, G2, G3, something like this. So here also the source code we are treating as a some kind of module. Okay. So therefore, that is why it is called, let me write M1 is the name of that particular module. Okay. So original name is FP underscore GL. In the Verilog point, in the test bench point of view, this is some kind of module name. Okay, M1 like M1. Okay. And we have to mention what is the vectors that we have used here. So the similar fashion that we have to give first, I'm sorry. Similar names that we have to give first A, B, C, sum, C out. The same way that we have to give. That means first three are inputs, second two are outputs. But you should not change that. First you give, for example, okay, give B, A, C, C out, sum, something like this you give. So it won't give you logical error. Okay. But the output will be wrong. Output will be wrong. There is no doubt at all. So if you change something like this, it won't give you errors. Won't give you errors. Okay, please remember. But instead, if you write something like this, first you write sum, then A, then B, then C out, then C. If you write something like this, okay, so obviously it will give you the errors. It will give you errors. Please remember that. So I'm changing the A instead of ABC, BAC. Of course, those are also inputs only, but the changes of ABC is there. And later I change to C out and sum. But the output will be generated, but wrong output you can find. But whereas in the second case, as you can see here, this will be actually a wrong output. That means the error will be produced. Why it is so? Because sum is actually output we have declared. Okay, but we are connected. That one is as a input signal. So therefore, the port mismatching will be there. Okay, port mismatching will be there. What does it mean? So I'll write here. So here, what we are seeing that. So instead of here is A, if you write sum here, so sum cannot be generated there. Okay, that's what it is. So port mapping is the problem here. So that means that here, if you see, here A is required, here is A is required, B is required, C is required. But you are generating for sum. Next, what you are generating? Next A, next B. Here is A, here is B. So for A, it does not have any problem here, but there is a problem here. Why? Because it is an output signal. It is an input signal. Okay, the port mismatching is there. Okay, so please remember that point also. Okay. Just a second. Okay, so we'll write here. What is the signal here? Is that it's called A, B, C. So first A signal I'm writing here is so same names that we can give A, B, C, sum, and C out. Please very carefully you have to write this statement. Okay. So after that one A and B and C has to be generated. Okay, so for that one, as everybody knows that as previously I told you, A, B, C, something like this. Okay, 0, 0, 0, I have to generate 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Something like this I have to generate these signals. Okay, so but instead of writing the table here, it is not advisable. So better to write in the form of a waveforms. So A is, you can see here, A is you can see here A is 4 zeros and then 4 ones. Okay, so right here is A is 4 zeros. So 1, 2, 3, 4. And then A is 4 ones. 1, 2, 3, 4. Okay. Na? So that means that here is 0, 1 second, 2 seconds, 3 seconds, not 3 seconds, 3 nanoseconds. Actually, the gate will be in nanoseconds only. 4, 5, 6, 7, 8 nanoseconds. Okay, so this is meant for A. So what about B for B? So writing test bench is very important. Okay, so in the given tool, it's not allowed you to write waveforms directly. So we have to write a test bench only. So you have to practice this test bench, how to write the program for that one. So many methods are there. So first we have to learn the conventional, then we have to go for different methods. Okay, next B is nothing but. So B is 2 zeros. Okay, next 2 ones, next to 2 zeros and 2 ones. What is the next one? C. C is actually what is the C value now? C is alternatively it is changing. Okay, so C is changing something like this: 0, 1, 0, 1, 0, 1, 0, 1, 0. Are you agree with me what I have done here? Okay, what I'm doing here, 0, 0, 0, 0, 1, sorry, 1, 1, 1. It is 0, 0, 1, 1, 0, 0, 1, 1. Okay, so it is necessary to write all the possible cases. Okay, so don't forget about to write. Sorry. So this is 0, 1, 0, 1, 0, 1, 0, 1. Okay, all the possibilities I have written. So as you can see here, first case is 0, 0, 0. So therefore, this is called 0, 0, 0, something like this. What is the next case? 0, 0, 1. Okay. So what is the next case here is that 0, 0, 1. Is it clear? So B, that is called C. So this information we have to keep it in our program. Okay. Okay. So let us write quickly. Initial. Okay, so for that one, we have to use the keyword called initial. Initial. Let us begin and end here. So within this one only, I'm going to write my main module. This particular test bench I need to write. Okay. So how do we start? Let us start with first A is assigned 0, B is assigned 0, C is assigned 0. So at 0 nanoseconds of time, A is 0, B is 0. So after every statement, I'm writing the semicolon, which means that yes, we can write one statement to another statement adjacent to each other. Okay, then C is equal to 0 again. Right? A, B, C. Okay. What is the next one? So therefore 0 time, this is what happened here. So at 0 nanoseconds time, this is happening. So at 1 nanosecond, you can see A is 0, fine. B is 0, but C is becomes 1. C becomes 1. It is observed at 1 nanosecond. Okay. So therefore at 1 nanosecond, A is equal to 0, B is equal to 0, C is equal to 0. Sorry, C is equal to 1. Agree? So at another 1 nanosecond, that means 2 nanoseconds. Another 1 nanoseconds, we can write it here is by using the another one means we have write one statement. Ash symbol is meant for delay. Okay, ash 1, I'm writing in this way. So therefore A is equal to 0. here at 2 nanoseconds, what is happening here? A 0, but B becomes 1, but C becomes 0. That's what you have to understand. A 0, B becomes 1, and C becomes 0 again. So like this, how many number of possible statements are there? Those many number of possibilities that we have tried. So I write all these things quickly as we understand this concept. C is equal to 1 again. So another 1 nanosecond. A is equal to 1, B is equal to 0, C is equal to 0. So another 1 nanosecond. A is equal to 1, B is equal to 1, C is equal to, sorry, it's better to write here is 0. Okay, here is the 1. So another 1 nanoseconds, that is 1, 2, 3, 4, 5, 6, 6th nanosecond, A becomes 1, B is 1, C is 0. So lastly at 7th nanosecond, so you can see 7th, this is 1, this is 1, this is also 1. So at 7th nanosecond, okay, A becomes 1, B becomes 1, C becomes 1. Okay. At 8 nanoseconds, I want to stop my simulation. Up to this point, I want to stop my simulation at this 8 nanosecond. Okay, so for I can write here is at another 1 nanosecond. That means 8 nanosecond. I want to stop my simulation. $stop is the keyword I'll use. Simulation I want to stop. $stop. As you can see, at 8 nanoseconds, I don't want to see any kind of output. But up to 7th nanoseconds only, sorry, up to 8 nanoseconds only, I can see. After the 8 nanoseconds, I don't want to see any kind of output. Okay, that's it. So that is how we have to write the test bench for this one. How many statements are there here? So far, how many we have written? So we consider this is the 2 second point. So this is the module instantiation, third step, and the declaration of the defining the variables of A, B, C is the fourth step. Only 4 steps are required. Okay. Is it clear to all of you how to write a test bench for this one? For any circuit, in fact, whatever the circuit that I have mentioned there. So this is the simplest way to write the test bench for this. Okay. So we have defined the source code. We have defined the test bench. I hope you understood this thing. So before going to the next problem, I want to show you how to run this one in my machine. Okay, so I have a tool with me. I have installed in my laptop. I will try to um, execute this program in my main program in my laptop. Okay, so the similar way that you can do it also. Okay, so let us start the thing. Start this one. So meanwhile, if you have any doubt, please let me know. So this is the software. Okay, Xilinx Vivado 14.4 version. Okay, so are you able to see the screen?
Yes, sir.
I will. Desktop I want to show. So this is my desktop. You can see here. So you can see that in the desktop, my desktop, you can see the Vivado 2014.4. Okay, just double click on this one. You can find Vivado. So if the screen is visible, Vivado screen, please let me know. So screen కనిపిస్తుందా? Vivado software? No. Okay. Stop sharing. Now it's okay. You are able to see my screen. Okay, the same procedure that I have shown you in my videos, previous videos, but we have to do it for adder. Okay. So let us try to write a Verilog program in Vivado software, and we are going to execute that program. That means we have to simulate that program, and we need to synthesize our program also. Okay, so two things that we want to do it here. One thing is simulate our program. Second one is synthesizing of our code. Okay, whatever the code is there, that must convert it into hardware. So how do we do this one? So let us create a new project here. So go to the next. So let us give the name of this project is lab number 3. Lab underscore 3 related to full adder. So it is there in this particular location. Go to the next. So RTL project that I'm doing here, not post synthesis and everything, but as soon as that means for the description purpose, for the simulation purpose, we use RTL project only. Go to the next. So we have to choose one particular FPGA. Okay. So we have Arctic 7 FPGA is there in our lab. Okay. And Arctic 7 is the subfamily package. We can see that FTZ 256. Okay, speed grade we can choose it -1. Temperature is C. So this is what the FPGA we have. XC7800F. This is the FPGA. So the first one to XC7800T is the FPGA name. FTZ256 is the package. That means where the pins are available for that particular package. The speed grade they have given here. Okay, you can see here it allows it contains 256 input output pins are available. Input output buffers are 170 input output buffers are there. 63,400 lookup tables are there, and 1,26,800 flip-flops are there in that one. RAM blocks are there, DSPs are there, so something like this. Okay, so that means in our lab we are not going to utilize all these things. Only less than 5% of the FPGA resources that we use. In real time, you can use n number of things. So this is what our summary. Go to finish. Okay, you can see this is what the screen it is generated. So you have to go to the add source here. Add source. I want to create a design source. Okay, as I mentioned, the source code is we have to generate. That is called design source. So add or create design source. So we are going to create, not adding, but creating the source. So add is the key. Add design sources we do for structural simulation, structural modeling. We'll do later on. Go to next. So we have to create a file here. So let us write a file here. What is the name that I have given? FA underscore GL. So this is the name of the module that I'm giving. Okay, it's a local project, local to the project. Fine. Okay. So this is the .v file stands for Verilog file. Okay. Just finish it. It is asking the inputs and outputs here. Okay, it is possible to write inputs and outputs here, but we will write it in the main program itself. Okay. So I don't want to change anything here. As you can see here, at this point. Okay. So that is generated. So I think I want to modify my environment, something like this. Okay. So this is the project summary is there. What kind of things are there? What is the name of the module? What is the FPGA that I have chosen? Okay, all these things are available. So this is for project setting and synthesis for the purpose of synthesis implementation. Everything will be there, but we don't want to consider this right now. Just you keep on concentrating on how to write a program. So here you can see FA_GL is created under the design source. Here, so double click on this one. You can see the skeleton here. Okay. So on top of it, nothing is required. Just I want to remove each and everything. But it's very important to understand that time scale directive is important. Okay, don't remove the time scale directive. Okay, so it should be there. Okay, that importance we'll discuss later on. So what are the variables that I have given? A, comma, B, comma, C, comma, sum, comma, Cout. Okay. I want to remove this one. So better I want to change the font size. Okay, so just right click on this one, change the font style. So better visibility is not good, right? So we have to increase to 16. How it look like? Okay, a little bit better, I think so. Okay, fine. Here I need to write my code. Okay, so what is my code is inputs are. You can see the color. The keywords are in different color. A, comma, B, comma, C. It's also possible to write the output here itself. Okay, because the semicolon we have used, you can write it there. Okay, sum, comma, Cout. Okay, so whiles are also there, of course. T1, comma, T2, comma, T3. We have to write in an XOR Z1 sum, comma, A, comma, B, and Z2 T1, comma, A, comma, B. Okay, I have to copy this one and I have to do it for a number of times. Paste it here. Paste it here. Okay, this is for G2. Okay, fine. G3 has to change. Yes, this is 2. This is called B. This is called C. So this is G4. This is called T3. This is called A, comma, C, right? Or C, comma, it doesn't matter. Last one is OR gate. G6. Sorry, G5. G1, comma, sorry, output is Cout, right? Cout, comma, G1, comma, G2, comma, G3. Okay, that's it. So actually space is not required. So if you give the space also, it doesn't matter. Okay, it's not at all a problem. How much space that you can give doesn't matter. Okay, but it's look awkward. Okay, so required spaces are we have to use. For the identification purpose, I'm using this way. So the inputs are something like this, outputs, intermediate wires are the something else. Okay, I want to save this one. You can see here the save. If you save, there is no problem here. There is no syntax errors here. That's the reason why I didn't find any kind of things here. For example, you remove this one. So remove semicolon, save it here. So you can see, you can at the left side, you can see that there is some kind of warnings and the syntax errors are there. So those errors must be identified. So just to go to click on this one. At the bottom, you can see some kind of problems. Okay, so it's saying that the error syntax error near the input. So whatever the near the input, something like that module is there. So there you find some kind of problem. Okay, So therefore, that's what we can identify that. And the semicolon is required. Okay, that's we put semicolon there. So you can see there is no errors now. No errors are there. Why? Because again, there is a near the semicolon, we have some kind of error. Near the semicolon means here only. So different line number also it will show you that. Okay. So we can write it semicolon. Bracket is we forgot. Yes, save. So there is nothing here now. There is no errors at all. As I mentioned that, for example, customarily we will write something like this: A and N, A and N. So is it right? So it is not showing any kind of color. Okay, if it is no, if you know, if there is no color, means it's not a syntax, it's not a keyword, right? So therefore you have to identify that. So it should be a keyword. Keyword has got purple color. Okay, so that's it. For example, you write as a capital Y, for example. So it is also not showing something like this. This is a syntax error. So if you write to save on this one, you can also find some kind of errors while you are running the output. Okay, it is not able to identify that one. Okay, so therefore better to write small errors. Okay, save this one. So what is the next step that we have to do? We have to write a test bench for this. So for that one, I have to go to add source again. So here we have add source. So go to this simulation source. So the test bench we can call it as simulation source. Okay, it is also code only. Just click on that one. Go to the next. Create. So better write what I'm writing FA underscore Gatelevel modeling underscore test. I want to perform the test. Okay. So okay, finish. So it is asking input outputs here. I don't want to show it here. Okay. So here you can see here. As you can open here, as you open here, simulation source is a design source actually. In the design source, we have one source file, and in a simulation source, in the simulation point of view, we have to open this one. You can see FA underscore GA underscore test. We double click on this one. Again, you can see here this skeleton is available here. Just you have to write a program here. Again, these things are not required. Okay, so here after this one we have to write. So brackets are not necessary. Okay, as we have mentioned that inputs are represented by register data type A comma B comma C. Okay, outputs are Y data type some comma C out. Okay, and we have to instantiate. Okay, FA underscore TZ underscore sorry TL GL underscore okay GL. It is M1 module number 1. First one is A comma B comma C comma some comma C out, right? So the same way that we have to give now initial let us begin. What is the input here now? A is equal to 0, B is equal to 0, C equal to 0. So this is the first statement. After that, I'm going to give you some delay. So here actually whether it is in nanoseconds or picoseconds, what is the delay that we are mentioning here? We are not writing 1 pico, 1 second, something else we are not writing. So that is assigned, whether this delay is assigned, whether nanoseconds or picoseconds is decided by time scale directive now, right? So the time scale directive says that it's a 1 nanoseconds. Whatever the delay that you write, that is in nanoseconds. That value is multiplied with 1 nanosecond, and the precision will be 1 picosecond. Okay, so therefore, precision point of view are not discussing here. Just it is a 1 nanoseconds time we are giving. Okay, just a second. So now A is equal to So we have to copy here. Paste here. How many times I have to paste here? So this thing. Copy. Paste. Paste here. 8 times I have 7 times. Sorry, 8 times I have to paste, right? Or 7 times. So paste here. Paste here. Okay, so this becomes 1. Okay, and now this becomes 1. Now this also becomes 1, and this also becomes 1. This becomes 1. This becomes 1, comma 1. This is 1. This is 1. Now we write another recipe also. Copy and then paste. So we have right end. So we have to write very neatly the program. Okay. So and finally, better I did write this simulation stop here also. Dollar stop. Okay. So finally and so is it clear? So whatever the program that I have written in the class is the same thing that I am writing here also. Okay. So first I have to check this one. To show you the errors. So you can see here, previously it is only one particular, two files are there. One is FA underscore GL, next FA underscore GL underscore test. But because FA underscore GL is inside of the test module, that's the reason why it is inside of that particular test. You can see here, this is inside of the test. If it is not inside of the test, that means something you have written wrong. Okay, please keep your understand that point. So there is no errors in the program. Okay, if you want to keep the errors in the program, just I want to say for sake of errors showing here the semicolon stop. So saving this one. So it shows some kind of error here. Okay, so go to the syntax error for here at this point, and you job maybe you click on this one, you can go to that point. Okay, so I don't want to waste further time. So save that one, and you can see. So this is how we have to do two programs here. One program is related to the test bench module or source code. The second one is the test bench. These two files should be there. Now we have saved everything. Just you click on this here. You click on it this one, test bench. Okay, and go to the simulation first. So you have to go to simulation. Run synthesis, run simulation. Just click on this one. Run behavioral simulation. It can show you an output. So you can see here the output is presented there. So many tabs are there. Not necessary to look at this one. Here, untitled one. Okay, just click on here. Just zoom to fit. You can see this one. Okay, see here. For 1 nanoseconds, what is happening here? For 0 nanoseconds, of course, 0 0 is there. At 1 nanoseconds, I think hope this is the 1 nanosecond, right? Yes. So it is at 1 nanosecond. At 2 nanoseconds, this is. What should be there at 1 nanosecond? At 1 nanosecond, there should be 0. A must be 0. Sorry. A must be 0. B must be 0. C must be 1, right? So why it is not happening? At 2 nanoseconds, what we have done, 1 has come. So why it is so? Let me check. So here, go to test bench. Oh, here. So at 2 nanoseconds, 001 is happening. So it's not required now. This is not required, right? Did you get what is the problem here I'm facing? My simulation output is not proper. Okay. So as you can see here, oh, sorry. As you can see here, so at 1 nanosecond, so C must be active. C must be 1. Okay. C must be 1 at 1 nanosecond, but it's not showing. 0 is showing. At 2 nanoseconds, C is equal to 1. It's not required. This is the reason why I stopped that one. I have saved again. Okay. Go back again, the run simulation. Run simulation. I saved already. Yeah. So I can see here, I hope we got right output. Okay, now it's fine. So I'll keep this one is a very lengthy one. So you can see here. At 1 nanoseconds, you can see C is equal to 1. Sorry, C is equal to 1. And my input patterns are 001, 010, 011, 100, 101, 110, 111. At 8 nanoseconds, that is stopped there. Fine, Banam. Now related to the sum and related information, the sum is equal to 0, carry is equal to 0, sum is 1, carry 0, sum is 1, carry 0, sum is 0, carry 1, fine, true. Sum 1, carry 0, fine. Sum 0, carry 1, sum 0, carry 1, sum 1, carry 1. That's it. So it is fully verified. Okay. Now the next question is, we have to see that whether it is synthesized in the code or not. So how do we see the hardware here? You can open the RTL analysis, open elaborated design. You can see the schematic for your program. Whatever the design we have done here, gate level circuit, that is synthesized as something like this. It is generate the generic hardware for your circuitry. So actual synthesis and implementation, we do it later on. Whatever the code is we have written, generic library, it uses the generic library, it can generate the hardware for us. So that you can see here. So it takes a lot of time. So as you can see here, the hardware is so whenever we have written something like this, it takes the generic library and it utilizes the as in hardware. Okay. Actually, I have written a 3-input exclusive OR gate, but it has in this particular library has got 2-input exclusive OR gate. Therefore, it has taken that one and connected something like this, right? And the carry output information I have given something AB plus BC plus CA, but it has taken according to the requirement. So according to the optimization point of view. Okay, it uses the available hardware and it will give you the sum output, something like this. Okay, when you synthesize, actual synthesis is here. So this actual synthesis, what will do, it takes the lookup tables related to the FPGA that we have chosen. Okay, we have chosen one FPGA. So it takes that FPGA related resources and it can generate the hardware according to the lookup tables. Okay, so I think let us do the synthesis, run the synthesis also. Okay, okay, I'm not doing any kind of constraint file, but let us see. It is a generic hardware, but in terms of the lookup tables, it can generate if you're using the synthesis here. Okay, so that's also, let us see that part also. So you can see here is a running synthesis design. So the last part is implementation only. Okay, that we are not going to do here. While we are implementing our design in FPGA, we'll do that one. So what is the synthesis? So no, I don't want to do that one. Synthesis is completed. Okay, fine. We'll go back to the synthesis. You can see here different type of reports are there. Okay, constraints, file, setup, debugging, and all these things, and go for the schematic. You can double click on the schematic. You can see that lookup table based hardware. So this is how it can be generated. Okay, so please remember that. So it uses lookup tables. Where these lookup tables actually come from? It is based on what vertex 7 FPGA, whatever the vertex 7 FPGA is there, that consisting of this lookup table trees are available there. Okay, so how many lookup tables also, as I mentioned previously, those many lookup tables are there. Input output buffers are also there. Okay, so the hardware is generated based on this one. Okay, one is RTL related, one is RTL based hardware. Next one is technology based. Actually, we can call it as a technology based or FPGA based hardware. This is okay. So I hope you understand this synthesis and simulation. Okay. So simulation has got only one step. Synthesis has got two step. RTL synthesis is there, and technological synthesis also there based on the lookup tables. I hope you understand this one. We stop it here today, and if you have any problem, please ask me through the WhatsApp. Sorry, through the chat box. So I'll clarify that one. So if it is completed, if it is okay, then try to solve the problem in the use the VPN and try to do it. Those who are not able to connect it to the VPN, okay, then try to write the program for the remaining circuits are also. If you find any kind of difficulty, I will tell you that. Okay.